Hello and welcome to the MIT System Design and Management Program's Systems Thinking webinar series. The SDM program is MIT's Masters in Engineering and Management. It's offered jointly by MIT School of Engineering and the Sloan School of Management, and it is specifically geared for mid-career professionals who want to lead effectively and creatively by teaching them how to use systems thinking to solve large-scale complex challenges in product design, development, and innovation. Today's presenter, Christine Miyachi, is a case in point. She graduated from SDM over 12, 13 years ago. She is a software engineer and system architect at Xerox. Before she starts, a couple of items, housekeeping items. Please make sure you're muted. If you have any questions during Chris's presentation, please type them directly into the chat section addressed to everyone. There will be a Q&A section at 12:45 to 12:50. And we'll go for about 10 minutes at that time. And lastly, you will be sent a link to the recording and slides once they're posted on the SDM website. It's usually within 1 week. So with that, I give you Chris Miyachi.
So this is a topic I have had on my mind for quite some time. And I will tell you when it became on my mind, and I've actually been thinking about it for a couple of years now, and I think the term overengineering, you've probably thought about if you've ever been baffled by a system that you didn't write, and you think, geez, this thing looks overengineered. So what I wanted to start with was when I was an SDM student, and this was way back in 2001. So it's been 15 years since I've been an SDM student, believe it or not. Professor Crawley, who was our professor in systems architecture, when we were done with the course, he asked us to come up with a list of principles we've learned about system architecture. And back then in SDM, the way it worked is we had half of the course in the beginning of when we first started with SDM, and then we finished up the course at the end of our tenure. So we really had a lot of knowledge and information about system architecture, among other things. And so he asked us to come up with a set of principles. 99% of us, including me, regurgitated, like very good students, exact wording of the principles that we learned and discussed in class. And I remember this was one of those moments that really stuck with me. There were one or two brilliant classmates that came up with their own very unique principles. And Professor Crawley drew them out and shared their principles with us. And now, 15 years later, I hope to come up with some of my own principles after gestating all this time as a student. So, first, I'll try to define what overengineering is, and I'm going to give you some concrete physical examples of overengineering. And then we'll talk about what overengineering is in software, and I think it's actually more prevalent in software. It's easier to do. And then we'll come up with some software examples. And then we'll talk about, is engineering really good or bad? Is it really that bad? There are some pitfalls with overengineering. I believe it can be bad. And then we'll talk about how to actually get it right. What is right engineering? And I want to start by saying that this talk is going to be a little less technical and a little more philosophical about how you would go about in designing something. And I also want you to keep in mind that we develop, as Lois said in the beginning, we engineer complex systems today. So what some people argue, what I've read in literature, is that you need complex solutions. So what I want you to think about during this talk is complexity a necessary evil given what we have to design to today? So this is one of the things that inspired me to do this talk. My boss said to me the other day, it was actually about a year ago, he said, she over-engineered it. And he was referring in this case to a set of requirements that were so overly defined, so intricately defined, that it crippled our ability to extend and further design our system. And in addition, a lot of the requirements written didn't even matter. So was this person at fault? Was this person a bad or unskilled engineer? And it got me thinking. I've always believed that when you have extra things in your system, be it requirements, code, hardware, whatever it is, you can spend a lot of time supporting those things and they don't give you anything back for your system. But in this case, this particular engineer, when she wrote those requirements, it was, maybe 8 years ago that she wrote them, and she was actually following the standards of the time. And so I don't think that if any of us, if he or me were writing requirements at the time, we may have written them at the exact same way. So here's a quote when I was doing research for this presentation. I think this goes almost too far, but let me read you this. It's actually was in a programming book, and it's inspired by a famous philosopher, Jean-Paul Sartre. Every line of code is written without reason, maintained out of weakness, and deleted by chance. And I don't agree with this quote but I think there is some truth to it, but I especially don't agree with the first part of this. Every line of code is written without reason. The reason I say that is because everybody writes a line of code to do something. They don't write it without a reason. They might be wrong in why they write it, but they have a purpose when they write it. Otherwise, they wouldn't write it. And when you write code, or when you do any engineering for that matter, there is a level of craftsmanship to it. There's a strong level of technical knowledge, but there's also a level of craftsmanship. So you really do have a reason to write every line of code. And of course, if you just kept writing code for no reason, then you would have an over-engineered and an overly complex and a mess of a system. But the second line, maintained out of weakness, that does happen when you have one of the terms I use for older systems is architectural decay. So you have a system, you write code, it works in the beginning, it's all clean, and then it grows over time, and there's stuff in there that you don't use, but you don't have time to take it out, so it becomes harder and harder to maintain, and you just leave it in there because you're too busy meeting deadlines. So I think that's what the spirit of this maintained out of weakness is. And deleted by chance is, oh gosh, I hope you wouldn't just delete things by chance. In software, there is a movement called the Agile processes, which is actually through all of engineering. And one of the principles is to have courage and go back and refactor and remove code and make it maintainable and have the courage to remove it. Because when you're removing code or making code maintainable, you're not necessarily working on a feature for a customer. And so you have to make time to do that, and it's very hard for organizations to do that given the competitive climate. But I know when we've done it, it has paid for us. So an example of the cost of writing, every line of code is a cost. And in my situation where I do a lot of system engineering with requirements, every requirement that we write comes with a huge price. So when I write a requirement, there's code to implement that requirement. There's test tools both on the server side and the client side. We also have to handwrite a test procedure. Then some other person has to run that test procedure. Then we might have to write code to automate that test procedure. And then we have to write the requirement in such a way to explain to other people implementing our system, because we might have several product lines, why that requirement's important, and maybe some more information about it. And we also have to make sure that that requirement is testable, which we'll do when we write the test, because we wouldn't be able to write the test. But you can see this is extremely expensive, lots of people involved, and if we don't get it right, from my experience, that we can go on and on and on about this. So you can see why he felt like too many requirements was over-engineered. So moving on to definitions. Here's a definition from Wikipedia. Over-engineering is the designing of a product to be more robust or complicated than is necessary for its application, either to ensure sufficient factor of safety, sufficient functionality, or because of design errors. So I like this definition. I think it's a good one, and I know in software we over-engineer our systems when we try to make code more flexible or sophisticated than it needs to be. And the logic is that if you make the design more flexible, you make it so it can be used to solve future problems. And this, the opposite of over-engineering, you might say, is simplicity, where simplicity is the art of maximizing the amount of work not done. So you fight to do the littlest amount possible to meet your needs. And you know, there can be problems with that, and I'll talk about that a little later. That's not a perfect solution either. The dictionary says over, meaning too much, engineer, design, and build. So it really just means I built too much. I designed it too much. Now, on the flip side, you can also under-engineer. And this happens to me even as an experienced engineer when I'm working in a new area. So I've been working a lot more in mobile apps. And I've been, for years I was on the server side of things, and so I'm doing a lot more in mobile apps, and I tend to under-engineer. My apps are very ugly. They're not aesthetically pleasing. Sometimes they don't do what they're supposed to do because I didn't know how to do it yet. And so that would be an example of under-engineering. But with experience, this is where over-engineering often creeps in, because you have the experience to see all the problems that could happen in the future. And that's where you say, I'm going to build it to be robust. And so where you can get stuck in a rut with what ifs, because sometimes you'll run out of time too, and you won't be able to properly finish your work for all your what ifs. One of the principles of Agile Manifesto is the Agile Manifesto. If you're not familiar, I have a link here. That's a very popular software process. It's related to lean processes. And one of the main principles is to deliver working software frequently, from a couple of weeks to a couple of months, with the shorter time scales. And at work, where I work, we do 2-week deliveries. Every 2 weeks, we deliver something. So what this gets you is a strong focus on what you need today. The problem with this, the criticism of this, is with maintenance, is that anything long-term, if you want to think about, well, that's great, we're delivering that, and this is what we need right now, but what about next year when we know this new standard is coming? Are we anticipating that? Are we doing any preparation for that? That has a long lead time to get prepared for that. And we don't often consider that when we're doing these 2-week delivery cycles. right engineering, which is the balance between under and over engineering, is difficult. Making it work first is important so that you reach a success, but you've got to have a balance of good development strategies to look at, what you need today and what you need long term. So what makes right engineering? Right engineering happens when you can predict the future. And the wise engineer is able to foresee the future and the consequence of their designs. And sometimes they get it right, and sometimes they don't, and there's a good amount of luck involved. I think, personally, it's better off building what is needed today. That said, I've missed opportunities by doing that. Sometimes you can change a system after it's been released, but sometimes you can't. In a lot of cases, we've tried to predict the future, and we even had features we absolutely thought we were going to do, and we built a lot of that feature, and then it stopped something got changed midstream, and the feature never fully got implemented, and we didn't want to rip it out because we thought it would come back, and it never came back. And there was one particular feature I just completely ripped out of our system. It was like 3/4 of the way done, but it had been 5 years. It was weighing us down. It was confusing our other platforms that were trying to build what we were asking them to build, and so I had to rip it out. So in another case, though, we've had 3/4 of a system in there for a really long time, years and years, longer than that last one. And the reason why we've kept it in is because customers are asking for it, and our management hasn't yet prioritized it high enough to do. And we just feel like it's going to be important enough someday. So even though we've had it in longer than the other piece I ripped out, this one is staying in. So it's really an art to decide what you want to keep in and what you don't. And like I said here, you don't always get it right. So here are some interesting concrete examples. When I say concrete, I literally mean concrete, because this is a building. It's in East Cambridge. Some of you might know this building. It's not far from MIT. Some of you who were students at MIT or live in the area, this is the Athenaeum building. I don't know if I'm pronouncing it right. It's the Athenaeum Press building. It was a printing press. It was built in 1895. It's a beautiful building. It is no longer a printing press. It's actually offices and businesses, and this is where my health club is. So if you can see over here, this is Cambridge Athletic Club right back here. So it has arches in it. And arches are really famous for being over-engineered. They're way too strong for what they need to support. And there are some beautiful arches in this building. This building is also known for the tile arch system for self-supporting interlocking terracotta tiles. And then here's another picture of the arch. So if you're ever in East Cambridge, you'll see this building. It looks exactly the same, except it's surrounded now by much more tall buildings. So let's see, anything else right here? Yeah, it's on First Street and Second Street and Linsky Way, if you're interested in finding. It's near the Longfellow Bridge. So our arches are in a lot of our buildings today. They're there because they're beautiful, and they do function well, but are they over-engineered? So if you look at the Roman arches, the aqueducts were dramatically stronger than needed to carry a stream drinking water. The loading is self-weight of the structure itself, and some of the aqueducts still are resisting lateral earthquake loads. That's how strong they are. So the Romans had little understanding of solid mechanics, but what they did have is they had experience and rules of thumb of what loads they could take. And some other things they had were they had a lot of experience and intuition. They had a high level of craft, as we see from their arches. They also had slave labor. and slave labor led to a very conservative design. So if you have lots of great masons and lots of rocks for arches, rock and slave labor, arches are a natural choice. But if they didn't have slave labor, they might have been pushed to invent something else, because using that much quarried stone and manpower it's very expensive. But the Romans stuck with what they knew. They had lots of experience with arches. They got better and better at them, and the arches were also beautiful. So this was another principle that we used to talk about a lot in our system architectures. This was one, the form follows function was one of the ones that we spit out for Professor Crawley. But here's some examples of form precedes function. So this is a picture of the Big Duck. The Big Duck is in Riverhead, Long Island. And while I was preparing for this talk, I wanted to look for some kind of funny roadside attractions, and I picked this one. I found this one because I've actually been here because my grandparents lived in Long Island, and in the 70s, when I was a little girl, I used to go here with my grandfather and get eggs. And I can't believe that this is still here. When I was looking around for this, I saw it, and I said, I know what that is. And it's still around. It's an historic site. And so if the question here is this building over-engineered? Well, the form, if the person who built this, it was a duck farmer, Martin Maurer, and he built this as a roadside advertisement. So in a way, the building was the advertisement. So in a way, he did say form follows function. But if he was going to use just a store to sell eggs, he would have built a rectangular block with shelves and a cash register, and that would be the end of this. And I'm sure that site would not be an historic site. And I have a feeling that this was a lot harder for him to maintain. It's called ferrocement. It's like a form of cement, and I'm sure it's very hard to maintain. It's built in 1931, and it's on the National Register of Historic Places. So, is this over-engineering? When you look at this, you think this man was brilliant. This place still exists today. It's weathered time. If you looked at it in 1931, you would say this building form does not follow function in this case, and this guy did not build a very good store. If maybe you thought that he attracted people, but the store inside's way too small, and he really didn't do the right thing. But yet here it is, standing today, standing the test of time. A little bit more on form follows function. It was the first phrase was from the American architect. He was from Boston, Louis Sullivan. He was talking that a style of architecture should reflect its purpose. And that made sense at the time and continued to do so for a lot of objects. But there are objects today that don't really follow that. Like if you saw an iPod today, is that really form follows function? I don't know if you would know what that is. If you looked at it, it's so small, and yet it's a brilliant device. And is it over-engineered? It's not over-engineered. It's got the minimal amount on it, right? Smartphones are another thing. They look like phones, but they do so many other things. They don't look like clocks. They don't look like alarm clocks. They don't look like music players, and yes, they are. So, okay. So I wanted to point out that with Apple products, Steve Jobs was one of those people that had the ability to see the future. He had the ability to engineer products that we didn't even know we need that stand the test of time. So, moving on, software examples. Here is a principle I'm hoping that I'm going to actually show you a technical example of this. So this is a principle that we follow in software called the single responsibility principle. And it says that every class, and you can think of a class as a module or a thing in a system, should have a single responsibility over part of the function in the system. And that function part that the class does should be encapsulated. So in other words, you can't go inside and change it and fiddle with it. And that class should do that and only that one thing. So there, and then it goes on further. It says that class or module should have one and only one reason to change. And so the talk of this principle is that if you do this, you prevent over-engineering. So you would only create things that have one and only one responsibility, and then they would work together in a whole system. And in software, this is particularly example because you could just write a straight functional set of spaghetti code, and then over time that would be really hard to maintain. And I'm going to switch and show you an example of this. So here's a web page. It's a menu. This is an app that I'm working on right now. This is a mobile app I'm working on. And the customer gave me this web page, and it's a simple web page, and it has a lot of data on it. So I'll show you what that web page looks like. It's right here. So it's the whole web page. It's got all the data of the menu. It's got everything about what, even if you don't know HTML, it has both the data and it has how that data should be displayed on the page. So that's all in one page. So as a new engineer, this to me looks very simple. I see everything in one place. It's simple and it works. However, this violates the single responsibility principle. The reason why is if the customer wanted to go in and add menu items, new menu items, they would add some, but they could potentially change some other stuff in here and break the way the page looks. If they accidentally deleted this, for instance, I won't do it right now, but if I was in there and I was changing this and I accidentally deleted something, I could break the web page just because I was changing data. Similarly, if I wanted to change the way the menu looked on the page, not the data, and I went in here and I could mess up the data and change that. So the way we do this is we separate the data out into a database, and here's some of the data separated out. I'll show you. Yeah, here's comments and so forth on, but each menu item has its own thing. And this is in a database, and this is running. And then I'll show you what the code looks like here. So the code for the page is a lot more simple. It actually loops through, and you don't have to understand this, but this actually is a loop here, and it loops through depending on how many items you have, and it just displays that. So this page is a lot simpler. It has no data on it, and it actually gets all its data from the database. So this demonstrates the single responsibility. The only reason I changed this page is if I wanted to change the way the website looked. And the only way I'd change, if I wanted to add a menu item, I would go in and modify the database. And I can't show you, I have the app running on my mobile phone. I've revised it, and it looks a lot different. I can't show it to you right now because I don't think we have video, so I don't see it on here, and I meant to ask, but it's all right. But it basically looks the same and on a phone, but it's a lot easier for the customer to change. The customer actually can go in and add menu items without me. They can go in and change the database, and they know they're not going to mess up the website. So that's the single responsibility principle. So does that make my system cleaner? Well, it depends on your perspective. I've got a lot more framework in this. The page itself is simpler, but I've got some JavaScript behind here. I'm not going to go through it, but I have to have some JavaScript. I have to have some what are called cascading style sheets. And I have to have a header and a footer so that all the pages look the same. And it's separated out, but in a lot of ways it's more complex so that I can give the customer the flexibility they need. So I think it's more robust for future things, but who knows, when I go look at this app 5 years down the line, did I over-engineer it? I may have. I don't know that yet. I'll find out in 5 years. So you can see how it's a slippery slope with this. It's never 100% clear. Another way people try to simplify things is buy versus write yourself. I've used this example in other talks. We used a product many years ago. It wasn't Rational Rose Real Time, but it was a similar product. And what this product did is you never touched the code. You would model what you needed the code to do, and then the model would generate your code, and you would never touch code. And there was a time in software engineering history where they thought that's where we were going, that everybody was going to be working with models and that models would generate perfect code. And we've not come to that. Maybe we will. I don't see it though. So what happened was we bought this product and it was beautifully clean in the beginning, like a clean sheet of paper, and it worked great, and everybody worked on their models, and then we had to do some other things that the models couldn't help us with. And so we started writing lines of code around these black things that we didn't know what they were. And it got so bad that we almost couldn't do anything anymore. And so a manager had it. He had it with the delays, and he said, rewrite it. So he gave us 6 months. He gave a small team of us 6 months. And we had to rewrite the whole thing from scratch and plug it in and we got it to work. So we created this line through these black holes, and eventually we got rid of these we ripped out all the code that was there. So what this takes, buying doesn't always make things easier. It can, but it also can make it harder, and this is a good example of that. All right, this is one of my favorite slides. I spent hours looking for this. This is a good one. Even if you're not a software engineer, you've probably written a program called Hello World, where it's your very first time in the language, and here you are in junior high. I think this might be Fortran or Basic, and you just have to print out the word Hello World. So here you are in junior high, and then your first year in college, this looks like, I'm not sure what this is. I think it might be C or Java, not sure. It's not Java, but something like that. So here you are first year in college. This, our longtime MIT people will recognize as Lisp, which isn't taught in college anymore, but this is your senior year in college. This example is old. And so this is Lisp. And then when you're a professional, this is C. So let's look and see what they're doing here. So it's like, why would you have any more than one line of code for printing out Hello World? Well, they made an array here, and they had one word be hello and one word world. And then they looped through the array and printed out the words. And then at the end, they printed out a line feed. Let's go to the next line. So maybe they wanted to do this because someday they want to put another word in between hello world, hello big world, hello cruel world, hello the world, whatever. And they did that anticipating that change. But you can see, as you maybe want to anticipate change, you're making this program more complex. And then the really funny thing is the seasoned professional. So this was supposed to be a joke, and saying, oh, you know, as you go along, you write longer and longer code. But sadly, or maybe not sadly, I see the reason for this. So let's go through this. And again, even if you're not a software engineer, you'll get this. So here's the main program right here, and it's creating something called a string. It's assigning it to the string hello world, and then it's sending it to the output and returning, and that's all it does. So the main program's pretty short. The complexity is with this class called string. Now, without going through the details of this, what this class helps you with is it helps you make sure that your memory is properly cleaned up and you don't overwrite something. And when you're working in the C language, you can have what's called buffer overruns or buffer overwrites. And you can also have what's called memory leaks, where you allocate memory and then you don't free it up. And when you have classes like this for strings, that can really help. So it shows this, and then in this case, this very simple program doesn't utilize that, but that's there for other people to use when it is needed. So. If you were only ever going to do something like this, then this is overengineering. But if you were going to do other more interesting things with strings, which you probably will, this is useful. I love this example. They have the full example has other examples of managers writing code. It's really funny, but I didn't include that here. Oh, this is a doozy. So this is a class. And you can't read it, and you're not meant to read it, but this is a window, the class for window, and this was in a Microsoft framework that it's obsolete now, but I wanted to include it. And Microsoft Windows today, their development system, the Windows object is as complex. But look at all the pieces to this. And this is an example of a class that represents a window on Microsoft Windows, and these are all the different properties and methods that you can call on it. And so you would never, in your right mind, I doubt you would use every single one of these, but depending on what you were doing, you would use swaths of these properties and methods to do your work. And depending on what you were doing, that would shift over whatever project you were on. But an engineer would have to know all these things. So is this over-engineered? It's hard to say. This is a window. People need to do lots of different things with a window object. So when you first look at this, when you're getting into the system, your eyes glaze over. But then you start finding the things you need, and then looking at examples, and you don't use everything. But this is what I see is very, very common in engineering, is we have lots of different ways to do different things for different people, and especially over time, this is what we end up with. All right. So what to do? I don't know if I may end up giving you more questions than answers. And here is why. So I did this table. There are some standard solutions to prevent over-engineering. But one of them I talked to in the beginning was KISS. This was one of our Professor Crawley ones that everyone had on their list, except my brilliant co-students that got theirs read in front of the class. Keep it simple. However, I have a blog, and some guy recently emailed me, and he was an MIT grad, and he had some pretty solid arguments. Hey, if you've got a complex system, you might need a complex solution, and that's just the way it is. I've always felt there are ways to encapsulate and make a system simple by layering or doing different things, and I think that's really hard to do. Especially if you have a large group of people and that group of people changes over time, I think it's possible. But like I said, we have a lot of complex systems, and it's very easy to build complex solutions for that. The other piece I talked about was YAGMI, you aren't going to need it, and this is related to feature creep. So, yeah, you aren't going to need it, maybe, but you might need it in the future. So how do you predict that? I'm sure that in some of the iPod, some people probably gave Steve Jobs and Apple feedback that no one's going to ever use this. It's too expensive. People said that about FedEx years ago when FedEx started delivering overnight. People were shocked by how expensive it was compared to the post office. And now we can't even imagine a world without FedEx. So you don't know, it's really hard to know what you're going to need in the future. And you can try to predict it, and when you get it right, it's a really good feeling. But you don't always get it right. Prevent software bloat. There's no buts with that one, but you've got to have the courage to keep it clean. You've got to have the courage to go back and rip it out. You've got to have the discipline and the management support to clean up your work. Consider not adding extensibility for future behavior or minimizing the number of configurable options. But darn it, you found out you really needed that robustness, and now you have to go back and add it in, and it may not be so easy to add in. And then you could design for more reuse, which I've done, and then only to find out years later I didn't need that reuse. Oh boy, I got to go back and rip it out, have the courage to rip it out, clean it up. The other one I mentioned was buy over build, and if you do that, you could be stuck with something you bought. And in our case, by the way, that company we bought from, they ended up going bankrupt. So we really had to do something. That was like another thing that, oh boy, we've got to get rid of this. We can't even support it anymore. A few other principles, Occams Razor. This means that simplicity is preferred to complexity. And like I said, this is ideal and we aspire to it, but it's harder to achieve in practice. Building a simple system for a complex problem is genius, in my opinion. And when you see it, I think we all aspire to it, but it's not easy to do. And here are some quotes that inspire this. Entities should not be multiplied without necessity. And then Aristotle said, nature operates in the shortest way possible. We can get a lot of inspiration from nature. And Einstein said, everything should be made as simple as possible, but not simpler. So that's that right engineering. And all of this results in a cleaner, purer design. And finally, another one is horror vacue, which stands for a tendency of filling blank space with objects and elements over leaving spaces blank or empty. And it's Latin for fear of emptiness. And an example of this is when you go in, there's a place in Cambridge, I don't know if it's still there, it's called $1 a pound. And it's just mounds and mounds. I used to go there when I was a poor student, and it's on Broadway, and it's mounds and mounds of piles of clothes, never mind folded, piles in cardboard boxes. So contrast that with very high-end merchandise on Newbury Street with very clean displays. There's higher value to that. An example I love to use is, I know this is blurry, but the Google interface is so simple, and they've resisted changes over time, and the Yahoo interface is complex, and I don't think it's changed all that much. It's just a busy interface, and I guess they rearrange things all the time and use slightly different colors, but the Google one is almost identical. And Google is really praised for their simple interface. So finally, at the end, what are my principles now after all of this? And this is just in overengineering. So my principles are, I like to study the system I'm working with over time. That is, I look at the system and I say, what area of the system changes the most? And that's where I build the robustness. So it might not be for the new feature and thinking about what could change in the future. It depends on looking at the overall system. Is that new feature part of something that changes a lot over time? And when you look at our system, we have, in any system, you'll have areas that change a lot and then areas that are very stable. And the changing areas are where you want to build robustness. And by the way, where it changes, that can change over time. And as an example, for a while in our system, we were adding a lot of new functionality, a lot of new things all the time. And then we stopped that, and we wanted to get our system, we stabilized our system, and then we got it working across more product platforms. So we weren't really adding functionality, but we were putting it on different platforms and tweaking the way it worked. And different sections of the system changed in that case versus just adding lots of new functionality, user functionality. Second principle, brawl, and we literally brawl, and if you want, you can ask my boss. He's, too much to his dismay, I brawl in an effort not to over-engineer. And this is a good fight to have. I say be professional, but this is a good fight to have with your coworkers. Vet your design ideas with others, and fight to put. If someone wants to add something new, fight to keep it simple. Fight to keep it as little as possible, and see what you get. See what comes out of that. And regardless of, the fact that we are experienced engineers, use your knowledge and experience and consider the future. I think that's a valuable thing to have. Yes, it might cause over-engineering in some cases, but when you get it right, it's serendipitous. And finally, have courage. Have courage to make mistakes. Have the courage to study older systems. And there's Grady Booch, who's a computer scientist. He has a software archaeology project where he's looking at old software systems and studying how they worked and how they were designed. And I think that's a really exciting effort, and that's what you have to do with your own systems, because many of us are working on legacy systems. And when you study your systems, that's where you get the experience, and that's where you get the ability to predict the future. Thank you.
And thank you, Chris. Folks, now's the time for Q&A. If you have any questions, please type them directly into the chat section addressed to everyone. And while that's happening, just a reminder that you will be sent a link to the recording and slides within about 1 week. I would also like to give you advance notice of our next webinar, which will be 2 weeks from today, November 14th. The topic will be logistics that learn, a dynamic engine to drive a smarter logistics future. This will focus on last mile logistics, and we think it will be really interesting to people in virtually any industry. Again, that'll be November 14th, and you will get a notice about that. All right, from Adam Hathaway, it sounds like you are skeptical about Agile and good systems engineering practices. Can you speak a little bit on this?
Yes, I'm sorry it came across that way. I guess I am a little skeptical, but not. I mean, Agile, I'm a big proponent of. I am, and we've been using it for years. And before we started using Agile, we were using a Waterfall method. And for those of you not familiar with Waterfall, Waterfall is when you do all your requirements up front, and then you do all your design, and then you build, and then you test, and you never go back, where an Agile method is doing an iterative process where you do a little bit of design, deliver it, a little bit of requirements engineering and design and deliver, and you do it in increments, and you get feedback on every step of the cycle. And I'm a huge proponent, and everywhere I go now, my kids now, I was talking to Lois before we started, my daughter's an engineer, my son's almost going, he's starting to work as an engineer, and they're all using Agile processes in their workplace. So it's really common. The only, one of the problems with it is you can throw away some of the practices that were really strong with Waterfall, like solid documentation, like doing an architecture up front. Sometimes when we started Agile, we stopped doing some of those things. We stopped doing really solid system testing. We were doing unit testing, but not overall system testing, because we were delivering little small bits of the system. So we were testing that and not doing bigger system testing. So you have to make sure that you still do some long-term thinking with Agile. So I'm a big fan of Agile and lean processes, so that's not. But I do appreciate your question, because I am giving you more questions than answers in my talk, so I apologize for that. But hopefully you'll come up with your own principles, like Professor Crawley challenged us.
Thank you, Chris. Our next question is from H. Greiser, who says, we are trying to start Agile on systems that include a lot of hardware. Do you have experience with that you can share?
Yeah. So with hardware, you really do have to do, depending on how hard your hardware is. So if you're able to inexpensively prototype and test lots of ideas out, you can do that and use Agile processes. But you may not have that. So you may really have to do a lot of waterfall-like up front, where you design things up front. But let's take an example of a building. A building, you can't build an entire building and ask the customer, do you like it? Oh, you don't like it? Let's tear down this wall. So what architects do is they do models, and drawings, and then now they have 3D simulation for customers that's inexpensive, that can change really quickly, and that gives the customer a way to really see what things are going to look like in the end. So that's how we deal with it where I work. But if you've got, let's say you have to make a decision on what, like we build multifunction devices that print, scan, copy, and fax. And we have to decide pretty early on what platform we're going to be developing on. That's what I call a meta decision. And so once that's set, and that takes a lot of experience, that's done at another level, and there isn't a lot of experimentation that's based on experience. So I hope that answers your question.
Thank you, Chris. And the next question is from Ben. Can you please comment on how you get refactoring prioritized within your 2-week sprint?
Yes. So what we do, we have something called an epic. So we have stories. This is the language we use in my workplace. We have stories, and stories can be done, they're broken down into a level that they can be done into a 2-week sprint. So we write a story, and a story has the language of, as a user, I can push this button and a web page will pop out, something like that. But we also have epics, and epics may be like a full feature. So you can do larger epics and contain stories, but then we also have what's called there's spikes. Spikes are research, and then we have another thing called defects. And spikes and defects are, if you have a code that needs to be refactored, a lot of times it's related to a defect, and or you have a spike where you have to research how long it's going to take and how you're going to do it. But you have to make a convincing argument to management, or a lot of times management understands that you have to refactor code. And it's not, it's going to be part of what you have to also have other activities where you're delivering stuff. That's what makes that really, really hard. So in our case, the case I did that took us 6 months to do. And then when we were able to, and everyone around us was delivering code still, and that old system was in there. And then only when we did enough testing and we could take our module and plop it in and no one else could tell, that's when we could do it. But it takes courage in management to wait. You know, that's a lot of resources to tie up for 6 months. There was, 2 or 3 engineers on it. And it just, I don't know how to, it's like eventually you could make a financial case. We didn't have to in this case, but you say, look, each engineer spends 3 days trying to add 2 lines of code where it should really only take about 10 minutes, and look at what this is costing us. You can do spreadsheets, which I've done before, successfully and sometimes not successfully. So it isn't an easy thing, but that's where that courage comes in.
Thank you. We have time for 1 or 2 more questions. Chris, are you able to go over for about 5 minutes if you need to?
I can go over 5 minutes, yeah.
Thank you. Okay, from Sonal, who writes, the needs of downstream systems such as data warehouses and reporting often conflict with emergent architectures of upstream applications. Those conflicts sometimes lead to over-engineering upfront. Is there an approach or model to guide such negotiations?
What the example that I'm thinking of is full stack development here. So you write, what I mean by full stack development is that there are all kinds of technologies that allow you to write code for clients like mobile apps and web pages, and then there's the code on the server side, which actually does computations on the data, and then there's the database side. And I think that's the root of your question, is like, as these things are changing, how do you deal with those changes? The only way I really see to do that is if you're writing something and upstream changes, you're going to have to go back and change your downstream. You're going to have to, unless you don't want to use those emergent architectures. There's really no way around that. And I think what you're saying is, well, you could make them really flexible, and you could, but you don't know what it's emerging yet. Until you know that, you can't build in that kind of flexibility. Also, I guess it depends on if that's an area of your system that you know is going to change a lot. You might be able to build in the flexibility, but it's not an easy thing, and especially in something like full stack development, the technologies change so fast that it seems like, and there's so many different things available and so many technologies available that it's hard to keep up. I don't know how anyone really knows at all. So, yeah, it's a good question.
Okay, and before we get to the last comment, more of a comment than question, I just wanted to thank everyone for coming and remind you that you will get a link to the webinar recording and slides within about a week. And for Ben, check the chat section. Eric Hankowitz down at the end has made a suggestion for you. The last comment is from Kevin C. And I think it's a very nice way to sum up everything. He says, your discussion about CRISPR pure design reminds me of Blaise Pascal's quote in a letter to a friend back in the mid-1600s. Quote, I apologize that I have made this letter longer than usual because I have not had time to make it shorter. Any comments, Chris?
Yeah, I did. I was reading that. I really love that. And you're right. It's a lot harder to make it cleaner than not cleaner. But, you know, it's funny. I was talking to my son the other day, and he was doing an assignment, and he's taking an AI class, and he said, my code is so messy that it actually is causing me to go slower. I would have finished it if I had taken the time to make it cleaner. So it goes for even the individual programmer, too. If they made it short, if they took the time to make it cleaner, they'd be able to get through the assignment shorter. And I wanted to also comment on the Eric Hankowitz comment, which is related. I really like, my boss would love you because he always forces us when we go into something, we'll be changing one particular thing and he'll want us to clean up the whole piece of it, everything in there, things that are unrelated to what we're doing. He drives us nuts, but that's exactly what he lives by is leave your code cleaner than what you found it.
That's fantastic. Thank you, everyone, for the great questions. Chris, thanks for yet another wonderful webinar. For those of you who are listening to Chris for the first time, she has recorded several webinars for the series in its 6 years, and I will include links to those in the follow-up email that I send to you when the links to the recording and slides are ready. So thank you all, and Chris, I definitely want to book you next year as well.
Thanks. I'll send you a date.
Have a great day, everyone.
Bye-bye.